All right, we're Team Jackson, and this is our presentation on deducing errors. All right, so reasoning about runs. Use deduction to find what is relevant. When receiving an unexpected value, trace through the code and identify lines relevant to the value. Separate the lines of code into relevant and irrelevant lines to faster identify the issue. Sometimes parts of the code remain constant with runs, while some changes with each run. On the right, we have an example of this being put into practice. So, for example, if there was a problem with the simple interest function, you would start from the return statement here, and then you would probably go up to here and see that the simple interest isn't changed, and then you see what's affected by the simple interest, and you just do this for each function. I will point out that on the right, pretty much all the lines are relevant, but you can see how this can be put into practice later on. This is a simple diagram on control flow. On the left, we have a program that basically identifies whether a number is even or odd. So you can see there's an if and an else statement. On the right is the example of the control flow diagram of the execution paths of this program. So control flow. Most pieces of code can be neatly broken down into templates. By subbing in the literal code, conditions, body, etc., one can represent most code in a control flow diagram. Recursively stacking the structures allows for a complete picture of the entirety of the program. On the right, there's an example of some of the control structures available that can be represented in a control flow diagram. So as you can see, each control structure has a condition and a body, and so you would just sub the literal pieces in that. These are pretty much all the basic control structures. There are more, but these are the ones that are used in most other languages. Now the problem with control flows. Jumps, unconditional transfer of control, can make control diagram unstructured or difficult to reason. Most programming languages avoid direct jumps. This is where you basically give an address, and that address is somewhere in the program. So you would just transfer the control power over to that exact location in the program. Indirect jumps, like a jump, but the jump location is computed rather than absolute. Even more difficult to represent with a control diagram, since it could theoretically jump to anywhere in the program. The best example of this is like a pointer in C++ mainly. So basically, you would just hold an address of another instruction. So this is really hard to debug, since essentially you could put anything in that pointer, and you wouldn't really know how to write it out in a control flow diagram. Dynamic dispatch, constrained form of indirect jumps used for methods of classes. An example is like a shape.draw method. This is used, it's basically calculated at runtime, since you're calling a specific object and using that function on it, and it changes on each, execution. And exceptions. Coding with exceptions causes the program to transfer control to either the caller or to handle the exception. This does not guarantee the function ran to completion. So an example of this is like a try-catch statement. So if the try succeeds, the program goes on, while if the whatever the body of the try fails, then it goes to the catch statement. And the problem with this is that you're not sure if the entire try statement executed, meaning that you can't be sure of what the state of the program is. So the problem with goto in particular allows one to reference memory addresses arbitrarily. Goto is not in itself bad practice, but can lead to hard to debug programs. Having a location accessible by goto makes it harder to know the state of the program. As a result, most languages avoid the use of gotos in favor of control structures. On the right, I have a simple example to illustrate this. So you can see that there's two goto statements. So if you were to try to debug A, it'd be possible that it came from either two execution paths, meaning that it could be, in this case, before it incremented or after it incremented +1. At the bottom, I have a little comic about how people generally use goto to just get out of hard to code situations.
Now we're going to take a look at the information flow, which is basically how information changes along a sequence of instructions. And more specifically, we'll go over how statements affect the information flow. There are a few different types of statements. First, we have the write statements. A write statement is one that can change the program state. An example of changing the program state is by assigning or writing a value to a variable. Next, we have read statements, which read program states. For example, if the value of one variable is determined by the value of another variable, then the statement with the calculation needs to read the value of every variable within it before it can do any calculating. I wrote a small snowball effect program you see to the right. Here we have 5 integer variables. The first, small, is assigned the constant value of 10. This is a write statement. The statement beneath it shows that medium equals small multiplied by a constant value of 10. That statement both reads and writes. It reads the value of small and writes small's value multiplied by 10 to the variable medium. The next 3 statements for the variables large, jumbo, and scary are also both read and write statements. They both read and change program states. Another type of statement is a control statement. This is a statement that can change the program counter. It basically can tell us where our next task is. Is it the very next statement, or are we moving to a different location? An example of a control statement is a while loop statement. To the right, we see an example of a while loop for my snowball effect program. This while loop reads the value of less and determines whether it is greater than 10. If the answer is yes or true, then the program counter goes to the very next statement. However, if the answer is no or false, then the next several statements are skipped. The same goes for an if statement or any conditional statements really. Lastly, in order to influence the information flow of a program, a statement must be executed. If there are any statements in a program that cannot be reached during its execution, then they're useless. All statements should have a purpose, and that purpose should in some way affect the information flow of a program. Here we have a program of the Fibonacci sequence. We see on the left the main, and in it an integer declaration and initialization, and a while loop which calls the Fibonacci function and prints its return value. Taking a look at the fib function, we see the 3 integer declarations and a while loop calculating the value for each result of the Fibonacci sequence. Now somewhere in this code there is a defect. The program ran with a value of n equals 9, and as the while loop called the fib function, all the expected return values were correct except when we got to the value of n equals 1. But in order to find this error, instead of grilling our eyes through every line of code, let's approach this with a more structured format. Here we have put together a table showing the effects of the fib function statements. In line 0, we see a statement that will write to the value of n and controls whether the next several lines of code are executed. In line 1, we have int f. This is changing the program state of the variable f to be an integer. In line 2, we see that f0 equals a constant value of 1. This is writing a value to the variable f0. Then we have a similar statement in line 3 for f1. In line 4, we have both a read and control statement. It reads the value of n, then controls whether the next lines 5 through 8 are executed. In the next line, we see that the variable n both reads and writes to itself. Line 6 reads values f and 0, writes to f. Line 8 reads the value of f, assigns that value to f1. And line 9 reads the value of f and sends that back to main. Seeing this table sets us up for the ability to see the dependency of each statement. There are two main types of dependency. We have control dependency, which is the statement that controls the execution of other statements, and we have data dependency, which affects the value outcome of other statements. Here we see a rough roadmap of the data dependency for the fib function. The direction of the arrows shows which statements affect other statements. Following the green line, for example, we can see that the value outcome of lines 6 and 7 are dependent on the outcome value of line 3. And following the blue line, we see that the return statement needs the value of f, which comes from the declaration of f in line 1. In order for a statement to be data dependent on another statement, two things must be true. First, it's reading a variable whose value was written in another statement. And second, there must be at least one path from statement A to statement B in which the variable is not being changed by some other statement. For example, statement A could be in line 2, and statement B could be in line 6. So line 6 is data dependent on line 2. Here we see a map of the control dependency in the fib function. The entry statement, or the call to the fib function, controls whether any of the declarations or loops or return statements of the function are executed. The while loop within the fib function controls whether the calculations are executed. Now that we've covered effects and dependency of statements, we can apply that knowledge to finding the error from before. Here we see a more formal top-down version of a program dependency graph for the fib function. Starting with what we know that when we call the fib function with the value of n equals 1, we are returned with an erroneous value. So let's backtrack. Here's where the erroneous value is sent back to main. This statement is control dependent only on the entry statement. Since we know that the function was called, we know that this return statement was executed. Looking at its data dependence, we see two statements that determine its outcome. First, statement 6. However, if we look at the control dependence for statement 6, we see that it can only be executed if n is greater than 1. Since n is equal to 1, statement 6 is not executed. Looking back at the returns statement, other data dependent statement, we track the dashed line to statement 1, int f. This is now the only statement that determines the value outcome for the return statement. However, while the statement in line 1 is a write statement for f, declaring it as an integer, f is not initialized with any value. Therefore, the computer gives this variable an arbitrary value. And that arbitrary value is what is returned when the fib function is called with n equals 1. Thus, through effects of statements and statement dependency, we were able to track down or deduce the location of the error without grilling through every line of code.
Okay, so I'm going to be going over program slicing, which is a technique used in software testing to simplify a program by taking a group of statements from the program which affect the value of a variable. So as you can see in this program right here, we're starting out with just a regular program, and then you're taking out all the unnecessary statements, which are the white boxes, and you're ending up with a simplified version of it. And the reason why you would want the simplified version is because it's easier to debug, test, and maintain, especially like the longer programs. So there are two main types of slices, a forward slice and a backward slice. And a forward slice identifies the statements that are affected by a particular statement. It is a group of all statements which are affected by the original statement. So as you can see in this code right here, if we start out with int sum equals 0, then we would only choose the statements that are affected by this statement right here. So sum equals sum plus I, and system.out.println sum. These two statements are the only statements which are affected by this statement up here. None of the other statements are affected by it. So a backward slice is all statements affected by the computation of a statement. In a backward slice, you group all statements required for that statement to work. So essentially you're just trying to make the most simple program possible, which still works and still creates the desired output. So if we choose this line, system.out.print line of I, our backward slice should be able to run and have the same output as it normally would have without without the unnecessary lines. So it would just be class example public static void main int I equals 1, the while loop with I less than 11, I equals I plus 1, and the original statement. So we don't need to require sum equals sum plus I because it doesn't affect the output of this. Alright, so for a forward slash example, we have some code here, and then if we choose the statement int mul equals 1, then all we have to do is just work our way down and find all statements which are affected by this statement. So it would be mul equals mul times a, and write mul, as these are the only two statements affected by this statement up here. And if we take the same code from last slide and perform a backward slice on it, and we choose write mul, then this program should still work the exact same, just it wouldn't write sum. So it would be int main, int mul equals 1, int a equals read, int b equals read, and then the while loop. But the reason why we include int a and int b is because it's required for the computation of mul here, which affects this. So you would have to include a and b. And then there's multiple slice operations. The intersection between a forward and a backward slice is called a chop. Chops are useful for finding out how a statement A influences a later statement B. So we have the forward slice from the previous slides and the backward slice. And what you do is you just find the lines which are the same, finds the lines from the slice which are the same. So it would just be int mul equals 1, mul equals mul times a, and write mul as these are the only lines which are the same in both slices. So this would be your chop. And then there's two more slice operations, which the intersection between two slices is called a backbone slice. A backbone is useful for finding out those parts of an application that contribute to the computation of several variables. So as you can see in this segment of code here, the red lines are the backward slice of sum, and the blue lines are the backward slice of write mul, and the green are from the backward slice of both, which are um, the the lines that are in both backward slices, which is also the backbone. So these are the lines required for the computation of multiple values, which are both of these. And then the difference between two slices is called a dice. A dice is useful for finding out how the backward slice of some variable differs from the backward slice of some other variable. So if we take the backward slice of write mul and write sum, then we would subtract write sum from write mul. So we would just delete all lines, all the green lines, and all the red lines because we're subtracting them, and we would just we would just end up with this segment of code right here with just these three lines. That's the dice. And then I'm gonna hand it off to Reed.
Using code smells. First, what is a code smell? Well, a code smell is a surface indication that usually corresponds to a deeper problem in the system. This is the definition given by one of the two individuals who helped coin the term. And as he put it, the idea behind calling them code smells is that they're characteristics in the code that look so bad you can actually smell them. Some common code smells are uninitialized variables, unused values, unreachable code, memory leaks, interface misuse, and null pointers, which we'll cover a few of. Also, by no means is this a complete list. And as the comment below makes its case, many of these issues can actually be addressed or resolved by using a style guide or following a coding standard. So uninitialized variables don't need a description, but why are they an issue? Uninitialized variables store unknown values, and these values may actually change with each run of the program, effectively making them random. The result of this randomness is that subsequent runs of the program may generate different errors. As you might imagine, that's a nightmare scenario for debugging. So you typically want to give your variables some initial value to avoid that issue. The question stands though, do we always have to initialize our variables? And quickly put, no. There might be edge cases where you don't want to, and not every compiler or application will enforce doing so. However, this has been maintained as good practice for a reason. It simply comes down to the fact that initializing your variables to some default value requires very little effort and prevents far more problems than it might create. Even in the situation where a default value does lead to an error, at least debugging will be much easier because each run of the program will consistently produce the same error. So unreachable code, why is it a concern? It's very straightforward. The code is unreachable, and the code should probably be reachable if you're putting it there. But let's dive into this a little bit more. Unreachable code is an error in logic or design that prevents portions of the program's functionality from being fulfilled. And one of the real reasons to be concerned about this is that it may not result in a warning or error, making it very easy to miss. Actually, I'd say that most of the time, unreachable code will not produce a warning or an error, which is the case with this example above, where the second print statement will never execute because the condition that leads to it, w is greater than or equal to 0, or w is greater than 0, is subsumed by the first condition, w is greater than or equal to 0. Now, there is an exception to the rule that unreachable code is a code smell, and that's debugging. Why? Well, sometimes statements may be inserted to identify a failure in the program. Essentially, you put the statement in a place that you believe is an unreachable state, and if that statement executes, you've identified an error or a failure. However, you still want to remember to take these statements out if for no other reason than maintaining the readability of the code later on. Memory leaks. So why is this a concern? Well, a memory leak occurs when a chunk of dynamic memory can no longer be deallocated because the final reference to it has been lost. Simple to understand. What damage can this produce? Well, a memory leak may actually reduce not just the program performance, but the system performance as well, and eventually could require a restart of the system at large. The good news, well, depending on the language that you work with most, is that it's mostly a concern for languages that lack automatic garbage collection, like C and C++. So how can we deal with memory leaks? How can we identify them? Well, you can do that by tracking the effects of statements on dynamic memory. For each statement, check whether it allocates, uses, or deallocates memory. You can also check whether the reference to that chunk of memory is still live, meaning it's accessible by other statements, in order to identify statements where a reference becomes lost. Also, look at the control flow graph. Is there a path from an allocation to a statement where the memory reference dies without first deallocating? That would be a memory leak. And in the example below, we can see very quickly, since it's a very simple example, where that memory leak occurs. In line 24, we see that P is given some memory. And in line 29, when it returns early, you're not actually returning the reference to that memory, you're simply returning 0. And thus, a memory leak occurs. So when it comes to null pointers, there is the good, the bad, and the ugly. The good of null pointers are the typical use cases. So initializing a pointer variable when a valid memory address isn't yet available, checking for a null pointer before accessing a pointer variable in situations where you think a null pointer might occur. And you can also pass a null pointer as a function argument when it's undesirable to pass a valid memory address. For the bad, this would be null pointer exceptions, things you don't want to encounter, but at least you can recover from them using something like a try-catch block. However, not every situation where you encounter a null pointer and try to reference it can recover from it, and this is where null pointers become ugly. So in languages like C and C++, as we're starting to catch a theme, if you dereference a null pointer, it actually leads to an undefined behavior. In many cases, it's simply that the program will terminate without giving any warning or indication to why it did so. And nothing will allow you to recover from this error. The program simply just terminates. Also, something to keep in mind is that some functions may unexpectedly return a null pointer, such as malloc in C, which, going back to the good typical use cases of null pointers, you should always check for a null pointer in situations where they might occur.
So in this portion of the presentation, I'm going to be talking to you about the limits of static analysis, specifically getting into static analysis tools. Turns out that FindBugs, which is a static analysis tool for Java, has a false positive rate of 50%. Why, as programmers, would we not write a better tool that has no false positives? Well, it turns out the reason for this comes down to the imprecision of these tools due to the vast number of language constructs. Each of these language constructs computes data dependencies differently and is therefore extremely difficult, if not impossible, to predict. The textbook goes into an example that you see here with a code snippet that has multiple different code smells, as talked about in the previous section, such as the uninitialized variable x at the very beginning, and then the potentially unreachable code here, write x. Now, the convoluted stuff that's in this for loop is basically looking for a perfect odd number. For those of you that don't know what a perfect odd number is, real quick, I'll define that. A perfect number is an integer where the sum of its proper positive divisors is itself. So, for example, the number 28 is a perfect number. Its proper divisors are 1, 2, 4, 7, and 14. If you add those numbers together, you get 28. So mathematicians have long tackled this problem to see if there is such a thing as a perfect odd number or an odd perfect number. And at this point in time, they don't know if there is one or not. They've never proven one to exist, but they have not been able to prove one doesn't exist. And so in this situation, this for loop may or may not terminate and reach the right X code. However, with something like this, these tools have to basically make a conservative approximation and decide at what point do I cut this off and just say right X is unreachable. Another example of approximations that these different code analysis tools, static analysis tools will do are things like an array. Any writing to an array could potentially influence any reading from that array, and any of the elements could potentially be affected. In this example, I'm showing you the function shell sort. And if we simply look at the dependency of the first element, well, in the first iteration, that dependency is some other element that's a pretty good distance away. But then each iteration, the elements get closer and closer together as to which dependencies exist. And when it's all said and done, the first element could potentially be dependent on every or any other element within this array. And likewise, any element in this array could have a data dependency on any other element in the array. And as you can tell, this exponentially starts to take off with crazy amounts of data dependencies. And these tools have to, at some point, draw a conservative approximation as to, I think that there's too many data dependencies here, so I'm just going to say that, yes, there's probably error. And so this is why you start to get these false positives. Some of the other data flow issues that could come up in dealing with these tools include things like indirect access, where a variable's location isn't determined until runtime. It's very difficult to analyze a program statically if you don't know where a variable is even going to be stored until the program runs. Pointers, as you can see in this examples, pointer analysis can start to become quite convoluted quite quickly. Here I'm showing you a very simple example where we are looking at 6 different pointers. And the first 3 seem simple enough, but as soon as you start getting into the last 3, this pointer analysis starts to get pretty complex. Most programs have a significant number of pointers in them, depending, again, on the language construct and how they utilize pointers. Optimizing compilers typically will assume that a pointer may actually point at all of the object addresses that are in the program code in order to be safe. And so you can see very quickly that a pointer analysis can start to get out of hand. And so once again, a conservative approximation has to be made here. Functions are another data flow caveat to these programs. Dependencies for a function could very nicely be determined if you choose to inline the function at every call site, each and every call site. But for large programs, and we're typically talking about large programs, this kind of falls apart. It's pretty impossible to do that, especially if you're going to deal with something such as recursion, where the function calls itself. And so these data dependencies within the function and within the arguments of the function can again start to get unruly and out of hand quite quickly. Another reason for a conservative approximation by these programs. Similarly, you have object orientation, where every instantiation of an object is going to create problems, or concurrency, where you have multiple pieces of a program running at the same time. If they both have data dependencies that are common, then there's no way to statically decide which one's going to go first or not. Other caveats that you have to concern yourself with are the source code itself. Source code mismatch is an issue sometimes when you're working with large teams of people. If you don't have proper version control on the programming, then you could end up actually doing analysis on a piece of code that has yet to be compiled properly, or it's an old version of the code. So it's very important that you have good version control and up-to-date compilations. Macros exist in most of these languages as well, such preprocessor programs like the include functions or the include preprocessor calls in C programs, that if you don't know exactly what's going to happen with those, they could produce some kind of uncommon behavior prior to compilation. And so that could impact your static analysis. When you're porting a program from one environment to another, undefined behavior sometimes crops up. Different compilers choose different implementations of certain constructs, and those might be defined in one environment that weren't defined in another environment. And so you may have programmed it on Linux, and it gets ported over to Windows, and some kind of undefined behavior crops up. And then aspects of the last piece of this, which we will get into more about aspects in the next chapter, but that is a piece of code that's woven into certain parts of the program, which really are a nice tool, useful for logging and debugging. However, it does introduce some arbitrary behaviors, and that can create some lack of understandability in the analysis of the code. So some of the tools that I've been talking about here, you heard me mention find bugs at the beginning of the program. CodeSurfer is another version for C programs. It's a pretty powerful program analysis tool. Pre-computes program properties, allows quick and precise analysis of the source code. This is one of the first commercial tools to actually provide precise interprocedural program slicing, as well as pointer analysis. And the thing that I really thought was neat about it was that it automatically generates these hyperlinks within the project. So much like whereas we saw in Holly's slides earlier, she drew such nice data dependency diagrams. This would do something similar where it creates hyperlinks and allows you to nicely follow the data dependency through the code. However, once again, you have to understand that there are caveats to these tools. They are going to spit out errors and things that, you know, it has to call some kind of approximation at some point, and it might not actually be an error in the program. So you're still going to have to go in and do some of the analysis yourself, probably by hand. These aren't incredibly common tools within the industry. They're very expensive, and the amount of actual productivity gain has yet to really be determined. So hopefully some of these tools will get better in time, but for now, that is what we have. Here are the resources we used. Ultimately was the textbook in this case, and that concludes our presentation. Thank you very much.